It's exciting to be in front of human beings again. My name is Katharina Rombach, and I'm presenting what we're doing in order to move towards a digital twin for railway wheels. Well, Cyprian just told you what he's doing with the onboard monitoring devices, and we're switching the perspective now. We're moving now on the wayside monitoring devices. So we actually have measurement sites. These are these wheel load checkpoints that are fixed installed in the railway tracks. And today I'm going to show you what we did with the strain gauge sensors, but we also have other stuff now implemented. Yeah, right. So the train travels basically over the tracks, passes these wheel load checkpoints, and gives us then punctual feedback on the condition of the railway wheel. And our vision is basically that we want to collect that data and also get data from other data sources such that we get a digital twin, a digital replica that basically replicates the health condition of the railway wheel. But of course we're not interested in the visualization stuff, but what is behind it. So we need to develop algorithms for fault detection, diagnostics, and fault evolution prediction. These are different tasks. However, we found in the beginning that we are always facing the same problems with the condition monitoring data, which is not necessarily specific to our setup, but I think most of you who work with real data can find this. So, and these problems we have identified as there are different factors that cause variations in condition monitoring data. On the one hand, of course, we have if the health condition changes. Does it not? Oh, okay, sorry. If the health condition changes, I can see it in my data. This is what we use when we do data-driven solutions, right? However, in operating industrial assets, especially if they are safety critical, we have hardly many faults. So we have also very little fault data available. So in our case, it even took a really long time to acquire a test data set. It's ongoing. And that is, of course, a problem because you want to train a model that is able to detect and diagnose these faults, but how do they look? We don't have the data for it. Of course, you can do an anomaly detection model that is just detecting anything that it has not seen before, but there are also other factors of variation in the data, and I just group them into ones that you can control because for example, I know at which load my train was passing the measurement site or at which velocities, but there are also some other factors that I can't control and I might not even know about it, right? And the problem is that sometimes if you don't know exactly how a fault looks like, it's hard to distinguish these kind of variations. And often we're faced with a situation that our data set is only partially having fault patterns available or is only covering parts of those other factors, basically. And the problem is obvious. If you have then a problem that is a model that is too sensitive, then if the operating conditions change, I have a false alarm, which I don't want. And if I have a too less sensitive model, a defect might not be detected. So this is what we wanted to approach as a basis for all of our 3 tasks of detection, diagnostics, and prediction. And we want to enable that we have models that are on the one hand very sensitive to faults, even if we might not necessarily know how exactly they look or we don't have a good representation of those, while still being invariant to those other factors. And we approach this with the first step, and we want to learn a suitable feature representation that does satisfy these 2 objectives. And this should then be the basis for these downstream tasks. How do we approach this? Well, we did this with contrastive feature learning, and some of you might know it, but I'm just going to give a small intuitive rundown. So contrastive feature learning, we basically aim to train a feature representation that groups similar samples close to each other in the feature space and dissimilar ones far away. So for example, I have a sample in my batch, I call it an anchor, and now I basically choose from my batch another sample that is similar. So in our case has the same health condition, but potentially or hopefully was recorded under other operating conditions. So we basically have the changing variations from different operating conditions. And we train the feature space such that these two samples in the feature space are grouped close to each other. And then we select a third sample, the negative one. We also pass it through our encoder model, so it's mapped into the feature space. And we optimize the feature space such that this negative sample is placed far away in the feature space. The negative sample, if you have labels available, is a sample that has a different label, for example. And this is how we train the feature space. And how do you select the positive and the similar samples? Of course, satisfying both of these objectives is the easier, the more representative your data is, right? So let's assume we have a data set with representing all future fault types and all other variations that we can have. We can satisfy that objective function, and we will most probably have achieved both of these objectives. However, if the data representation decreases, the difficulty of achieving both of these objectives increases. And we basically we're working with different data sets in order to test how we can implement this with varying degrees of data representation. So we did one study also with SBB together on railway sleepers, where we said we have sufficient data available, and we also have seen the faults. I will not talk about this in detail, just we applied contrastive learning, therefore in a supervised manner, where we selected the positive and the negative samples simply by the label. And this performed really well, way better than normal classification with cross entropy. We had a performance gain of 13%. But for now, we wanted to increase the difficulty by reducing the data representation. So to test that, we used a benchmark data set, because there we could control all of the factors, basically. And then we did the test on this bearing data set that has 10 different health conditions, so healthy, 3 fault types, and 3 severities. And we would do tests with limited data from other factors. So we would just have a subset of all of the operating conditions in that sense, and also limited fault data, so we would not include all of the faults that we have. So our task was it then we still wanted to enable reliable classification, but also detection of novel faults. So what we did, we trained the feature space as I just explained you, with the labels that we had, with the fault conditions that were represented, and we classified it and clustered it. The clustering is required if you want to detect novel faults. And then we did basically 2 case studies. In the very first one, we trained the feature representation on a subset of other factors. In that sense, it was other operating conditions. And then we would test it on the known operating conditions on a data set with the known ones and the novel one. So we could check objective number 1, and then objective number 2, we did the same just with faults. So we did train a encoder model on a subset of faults. So we used 7 out of 10, so we took out 3. And then we evaluated the model if it can classify the known faults, but also while clustering, can I detect the novel faults? And this we did. So this is the first test that we did when we trained it on a subset of operating conditions. And on the left, you basically see the feature space of the same model architecture, but optimized with a cross entropy loss. And you can see, we can see the different classes perfectly, right? But on the right-hand side, with the triplet encoder feature space, the classes are more compact and also more distinct. So we can see that also then in the classification results, both feature spaces are absolutely suited to do classification on it. However, if we cluster it, we did it with the density-based clustering algorithm optics, the triplet encoder feature space was way better suited. So yeah, T is always the known operating condition, a test set from the known ones, and TP is from the new one. So we did it with the second one, where we also wanted to see if we can detect novel folds. So the novel folds are the softer colors, so it's the soft gray, soft purple, soft orange. And what we can see in both feature spaces is that actually the dream would have been that the novel folds would be clustered also somewhere else, but this did not happen. However, with the density-based clustering algorithms, we were able to detect outliers on the right-hand side, and actually 94% of the detected outliers were actually novel folds. So from an operating perspective, if you get an alarm there is something novel, then in 94% it was actually a novel condition that we had not in the training data set. And this would maybe also be good to establish a wider data set if you then go and assess it. And this we could also see then in the results. Of course, we trained the classification model only on the known faults, so it can't classify the novel ones. But if we cluster it based on the triplet encoder, at least the known fault conditions could be detected again. And the novel ones were not detected as 3 individual classes, as we can see in the feature space, but they could be detected as outliers. So these were the 2 objectives that we wanted to test on this data set, where we could really control what is in the data. And then last, we were encouraged by it and wanted to move to our railway wheels, where we will not use any confirmed fault data for training the model, because we just have hardly any confirmed ones, and we really want to keep it as a test data set. And with regards of the other factors, of course, I know some factors like the velocity, the load and stuff, but I actually don't know. I mean, it's recorded in the wild, so I don't know what other factors exist. However, how do you apply contrastive learning on such a scenario where you don't have negative samples, you don't have faults, you don't know how a fault would look like? And we approached this by defining similarity and dissimilarity in time. So basically, our idea was that we wanted that a wheel, as it leaves the workshop, where it's freshly reprofiled, and it travels over the tracks to the next workshop, it does degrade, so the health condition changes, right? And it's still a healthy wheel, and degradation is not a defect, but can we still train a feature representation that is sensitive to these health condition changes? So we do define it as similarity in time, and the starting point is always when it comes freshly reprofiled from a workshop. This has, by applying it to time series and defining it by time has been done also by a research group from EPFL. Of course, we link it also to the vehicle, because then it correlates to the kilometers traveled. Yeah, exactly. And this is how we train the feature space, although we don't have faults. And then now, currently, it's ongoing work. We are evaluating how we can use this for detection, diagnostics, and evolution prediction. So I cannot show you a lot currently, but I will just show you one thing that we did, for example. So in the context of fault detection, what we did is we used the data. So we trained the feature representation on presumably healthy data, because we don't know other. Then we trained a one-class SVM, so we just did anomaly detection, trained a decision boundary where we would define something as healthy. Yes, I've seen that before. And defect, this is something anomalous. And what we did basically is we trained this decision boundary, and then now we can track the condition of a wheel as it travels over the tracks. So the wheel comes out of the workshop, it goes over the first measurement site, I take the data, map it into the feature space, and now I can measure the distance of this feature space to the decision boundary. And this is basically like we could say like a health index, and I can do this over time. And this gives me these plots. Unfortunately, I had to take away the x-axis, but it's on purpose. Right, and we have evaluated that for a few wheels where we knew that a defect happened, and domain experts did also look at the data and basically decided until when they would define something as healthy, that's the green area, or something as faulty, that's the red one. And we can clearly see, so the decision boundary is the dotted line in blue, and we can clearly see that the health indexes go basically crossing that. And in the first example, it's actually doing it in the transition phase. However, in the second one, that's currently the problem that we are working on. It does do it, but way later. So it's not hours later, I just say it's days later. And correct, so this is what we're doing now, and we're also, of course, doing this for healthy trajectories, where we clearly see that as the wheel actually approaches to the next workshop visit, the index comes closer and closer to the decision boundary, which makes sense on how we trained the feature space, and sometimes it also is then passing it, and currently we're trying to close the loop. Is it a problem of the model, or is it maybe, can we use other measurements about the wheel if something else was defect or not? Well, thanks a lot. That was it. I will end with the vision again, what we try to do, and just what I want to present today. We try to do it by learning a feature representation that can be used for all of these tasks. Thanks.
Thank you. Questions for Kathy?
Thank you for your very interesting talk. We should definitely chat afterwards. We're working on something very similar within SBB, so I'd love to hear your thoughts. But right now, you mentioned you're mapping some measurements of the wheel into a feature space. Mm-hmm. Can you go into detail on what measurements those are?
What you have seen today is the strain gauge sensors. So, I don't know what happened. Okay, we're back. We are from these wheel load checkpoints. These are measurement sites that are in the track. So we have 8 sensors at a fixed distance within the tracks, and they are strain gauge sensors. So we get that data, and we map each sensor measurement to a certain wheel. So the train passes, we get a full string of all wheels, and because we want to model really the condition of each individual wheel, we basically extract the measurements when the wheel was crossing each of the sensors. And then that's our 8 measurements of one wheel. Yeah.
Thank you.
Hey, thank you for the talk. It was very interesting. I was wondering if before doing the contrastive learning, you have any sort of data augmentation that you perform on the data you have.
You mean to compensate for the missing other factors, or?
Mainly to increase the number of positives you could have, because you say you have a limited amount of positive samples. Mm-hmm. And I was wondering if there's a way to do some sort of data augmentation to increase that number artificially.
Okay, so initially when I started there was a data set, but it was very selected, so it was obvious faults just before the workshop visit, and then we did binary classification, just classifying those from freshly reprofiled wheels, right? And for that, to increase the representativeness of the data set, we did do the normal data augmentation. But if you have something better in mind, yeah.
No, it was just a question.
Yeah, but we quickly found that this is I don't know, distinguishing a perfectly healthy wheel from one that is not perfectly healthy is not really what SBB can use, I guess. Yeah.
So just to fully understand, but you would say that doing the augmentation of that data you have on the checkpoints, for example, is complicated because by doing the augmentation, it might not represent a healthy wheel anymore? Or did I misunderstood something?
This is why I don't do it on that data. Because currently, this is basically why we don't, the measurements that we had in the first were just measurements that were visually wrong, but we didn't actually know what it was. So we're not using that. And why I don't do I mean, you know, should experiment probably with augmentation, but if you don't know how a fault looks like, it's a bit tricky, but I think a few data augmentation techniques would probably be good.
No, that makes sense. And I had another question. You use the time between, like the travel time between like a healthy and an unhealthy wheel, if I understood correctly, correct? Or not exactly?
Presumably they are all healthy. I'm
Okay.
only using data that was not reported as a defect for training the feature representation. I'm trying to get a sensitivity to degradation first, because the condition of the wheel does change over the time, and this is what I use. I'm not saying that it is 100% healthy, because we just don't know, yes.
That kind of answered my question, actually.
Okay.
Perfect, thank you.
Yes, thanks.
So are there this kind of wheel load checkpoints all over the Switzerland, or where are they?
Yeah, they're scattered around the tracks. If I say now a number, it will be wrong. But there are multiple of these checkpoints in the tracks of the system.
Do you get like similar data from all the checkpoints, or are there differences?
If there's a distribution shift of the different measurement sites,
Yeah.
I mean, the data per se is the same, but yes, the data from different measurement sites can vary a bit. It depends on the calibration, it depends on the underground, and it also depends on certain measurement sites are crossed in the different operating conditions. So they vary a little bit, but I don't know what the impact of these factors is that I just listed.
Okay.
Yeah.
One last question for Kati.
Yeah, so super interesting. Thank you. I live in Canada. What you were talking about, like uncontrollable kind of environmental factors. You do have snow here in some locations. I don't know if you have any sensors in locations where you have snow, but what would be your take on the challenges that would associate it to this problem if you have very kind of varying, if you have ice and snow and heat, like images in all these different kinds of conditions.
Yeah, I can only hypothesize because I did not evaluate that concretely.
You don't have it in your data, those issues?
I mean, I for sure have some measurements where snow was, but I don't know. Like, I did not evaluate that specifically, but especially, like, it depends on the modality, that the type of sensor that you're using. It's very sensitive to temperature. So that's certainly one of the factors. But yeah, I mean, if you have a full representation, I think you can use it. But if you don't, like if you then have condition monitoring data recorded only in summer, I would be very careful if it works in winter also.
Okay,
Yeah.
thank you.